Welcome back, everyone. Let's finally finish up Chapter 13 and cover Proton NMR spectroscopy, which actually earlier this term I heard you cover in lab to some extent. So you've probably been exposed already to some Proton NMR spectra. But that being said, I think it would be a good thing for me to walk you through several of them so you have an idea of what to look for. When we covered carbon NMR spectroscopy in Chapter 13, there were some ideas there that we learned that were relevant to carbon NMR that still apply here. We learned for carbon-13 NMR, there's such a thing as chemical shift, where the chemical environment around a given carbon-13 nucleus makes it appear at one or another place on the spectrum and show a resonance at a particular chemical shift. The same exact thing is true for proton NMR. The only difference is the chemical shift range is much smaller for proton NMR, whereas it was typical for us to see a carbon-13 chemical shift range of, anywhere around about 0 to 200 parts per million, or maybe even higher. For proton NMR, it's a much shorter chemical shift range. It's rare to see anything more upfield than 0 parts per million, and even rarer to see anything more downfield than maybe 14 or 15 parts per million. That's about the maximum. I don't think you'll find too many exceptions to that. So, but we understand about chemical shift, we understand about chemical equivalence, just as we saw one resonance for every chemically distinct type of carbon atom in a carbon-13 NMR spectrum, so we will see one resonance for every chemically distinct type of proton in a proton NMR spectrum. And we already went over how you can know whether any two protons are chemically distinct or chemically equivalent. I gave you a step-by-step method earlier in the chapter, whereby you change first one proton and then another into, let us say, a chlorine, and then you name the compounds. If the resulting names are the same, then the two protons are chemically equivalent. If they're different, then the two protons are not chemically equivalent. And later on, when we touch on some of the more complicated sort of splitting patterns, if the names are equivalent, but they differ with one being the R enantiomer and the other being the S enantiomer, then those two protons are what we call diastereotopic. Spoiler alert, in other words, a big mess. So we'll touch on that briefly later. Good, so spin-spin splitting, I've just mentioned, that's another new feature of proton NMR spectra, and also peak integration is a new feature. Largely, peak integration doesn't work with carbon NMR spectra because they've been broadband decoupled so that you don't get any spin-spin splitting. So that also kills off peak integration as being helpful at all for knowing how many carbons there are in a given resonance. So that's why you never got told that in a carbon NMR spectrum. You can get some kind of an idea in a carbon NMR spectrum from the relative heights of the peaks. Yeah, that's true, but it's only rather rough. There's certainly nothing exact about it. Good. So that being said, I'll assume that you've reviewed about carbon NMR, and that will certainly be helpful here. There is a correlation table in your textbook I pointed out here for all of the different proton chemical shift ranges. I do not recommend that you memorize those numbers, not to mention that I guess for us in spring of 2020, the exam will be open book anyway, so I doubly see no reason to do that. But I don't even know how helpful it'll be to even look at that correlation table very much. Those ranges there are only guidelines. They're just an idea of roughly where chemical shifts of that type show up most of the time. I would recommend, even with the exam being open book and open notes, that you instead look at as many proton spectra of, say, small to medium-sized molecules, as I say here in the book, using that website that I gave you guys earlier in the term. That's the best way to prepare. certainly look at the OWL questions, certainly look at the book questions, but the more proton NMR spectra that you can take a look at and try to make some sense of, that's the best preparation I can recommend to you. Students have come back to me later and said that type of preparation works. So there you are. You don't have to take it from me. Good. So that being said, let's look at a couple of, at first, very carefully selected proton NMR spectra. We'll look at chloromethyl methyl ether and methyl acetate, and I've given you those two structures over there. And what we learn is that, well, let's start with chloromethyl methyl ether. So I think you'll agree with me, there's two types of hydrogens here. The 3 on the methyl group are the same, and the 2 on the CH2 group are different from the methyl, but the same as each other. And so we would expect to see 2 lines on the, or 2 resonances on the proton NMR, and indeed we do. It also makes sense that the resonance for the methyl group is more upfield, more to the right on the spectrum compared to the other one, because these 3 hydrogens are alpha to the oxygen, and protons alpha to oxygen, typically we see them around at about 3.5 or 4, and indeed that's exactly where these are, about 3.5. Whereas these 2 are alpha not only to oxygen, but also to chlorine. So I would expect the effect to be almost additive. And so they, as a result, show up way down here at about 5.4. So 2 resonances at just about the exact chemical shift we expected. The integrals, or the areas under the peaks, are going to be relevant. And there's no way, of course, you can integrate a peak just by looking at it. So often you'll be given peak integrals as you see here. Just be aware again that the area under the peak is proportional to the number of hydrogens that it represents. So again, it's only proportional to the number of hydrogens. It's not equal to it. It's only proportional. All we get out of that is a ratio, that the ratio of these 2 types of hydrogens is 3:2. But simply from this spectrum, we couldn't tell if in the actual molecule it's 6:4 or 9:3, that type of thing. Wait, did I do that right? 6:4 or 9:6? Right, we can't tell that just by looking at the spectrum. So you will never need to be able to tell something that you cannot possibly tell. You don't need to worry about that. But do bear in mind that this only gives us a ratio. These integrals are proportional to the number of hydrogens there are. And you'll get an idea in the OWL assignment other ways that you might be given this information. But certainly if I feel you need to be given the integrals in order to be able to tell what something is, I will certainly do so. And this is normally how I do it. So other than that, a completely unsurprising spectrum. Moving on to the spectrum of methyl acetate, the methyl ester of acetic acid. Once again, you go look at the structure, there's just 2 types of hydrogen, one on the ester methyl, so this one's attached to an oxygen, and one on the other methyl, which is different. This methyl group is attached to the carbonyl carbon. This one's attached to oxygen. So you've got 2 types of hydrogen. Each set of 3 hydrogens is equivalent only within itself. The 2 methyl groups are non-equivalent, however. So we would expect to see 2 resonances. And again, protons alpha to oxygen, generally 3-something, maybe 4. And the protons alpha to the carbonyl, I normally look for them around 2, 2.5, somewhere in that range. Let's see how I did. Yep, there you are. So this will be the methyl hydrogens that are next to the carbonyl. And over here at about, what do you want to call that, 3.65 or 3.7, that's the ester methyl. That's the methyl that's attached to the oxygen. Now you'll notice again, it doesn't say 3H and 3H. And if this were on the exam, that's how I'd give it 2. All we can learn from the integrals is that they're in a 1-to-1 ratio. But it does not tell us the absolute number of hydrogens, just the relative amounts, the proportion of one to the other. Still, I think you will agree that's a bit of information that we don't get from carbon NMR spectra. Well, of course, like I said, these 2 proton spectra I picked extremely carefully so as to avoid spin-spin splitting. And if you've read ahead on spin-spin splitting, you can look at these structures and see why there's no spin-spin splitting. There's no adjacent sets of hydrogens. right? This methyl group and that CH2 are separated by an oxygen atom. They're not adjacent. And these two methyl groups are separated even further than that. So there is no splitting in these. We just get singlet peaks. But there is a phenomenon whereby protons that are on adjacent carbon atoms can, if you will, they can split each other. The phenomenon is known as spin coupling or spin-spin splitting. And we could get into the multiple spin states and draw little diagrams, and that's all fine. The book goes into that. But the upshot of it all, again, I want to keep this all very, very practical. The upshot of it all is in the simplest case of spin-spin splitting, when you're looking at a resonance for a particular set of hydrogens, that resonance will be split into a number of lines. It will not be only one line, not just a singlet. And in the simplest kind of splitting, the number of lines that we will see for a given resonance is the number of adjacent hydrogens plus one. So we would expect, for instance, the signal for the methyl group in this compound, which we're getting to the spectrum of this one next, we would expect the resonance for the methyl group to be split into two peaks because there's one adjacent hydrogen. These six are too far away to split. And likewise, I would expect the resonance for that hydrogen there to be split into 3 + 1 = 4 peaks, or a quartet, as we call it. And I think you will see that's the case in the spectrum of 1,1-dichloroethane. Whoops, it would help if I made these actually chlorines, wouldn't it? There we go, that's more better. So there's 1,1-dichloroethane. So as you can see, the peak for this unique hydrogen here, which by the way is pulled very far downfield by virtue of being next to both chlorines, so it's almost at 6 parts per million. And it might be a little bit hard to see, but if you stare at it, I think you can see that there are 4 lines here. Shorter, taller, taller, shorter. Oh, and we could go into the reason why the peaks are the different heights that they are. That arises out of something you probably looked at in high school math known as Pascal's triangle. And that will help you predict, if you want, what the relative heights will be, at least pretty close to that. But again, I want to keep this as practical and of immediate usefulness as I possibly can. Likewise, the methyl group is also no longer a singlet. It's split into a doublet, and you can maybe see 2 lines here. This one doesn't show up as clearly as the next one. I, of course, will never make it my goal to trick you. I would not be surprised if you look at the spectra from last year's exam, which I just uploaded, if there was one where it was hard to see how many lines were in a certain range. I just flat out told them, because it's not my intention to be tricky like that. I wouldn't withhold any information that I think you needed in order to solve the problem. Good, so that's one example. Other than that, we have the hydrogens in the methyl group. They're shifted downfield a little bit from where we normally see protons in a methyl group. Normally, I'd look for that between 1 and 1.5 maybe. Pulled down a little because the chlorines are somewhat close by, but not directly adjacent. Another example of a compound that shows spin-spin splitting, or does and does not show, is now not methyl acetate, but ethyl acetate. And so we see three resonances here, I should say. The sharp singlet resonance here, which integrates to 3 hydrogens, is for the methyl group that's attached to the carbonyl. And again, for that methyl group, there are no adjacent hydrogens. So it's not split, it remains a singlet. The protons in the ethyl group, the 2H resonance and the 3H resonance, so this would be the resonance for the CH2 in the ethyl group, this one for the CH3. Unsurprisingly, the CH2 resonance is quite far downfield shifted. It's at a little above 4 parts per million because that CH2 is next to the ester oxygen. And likewise, the methyl group on the end of the ethyl group is right around 1.2, 1.3 parts per million, very typical range for alkyl hydrogens. And again, notice that the methyl group that's attached to the carbonyl, right around 2 parts per million. 2 or 2.5 is very typical for protons of that type. But what about the splitting? Well, if we go to the 2H resonance over here, and we count how many hydrogens there are, well, there's none on this side. There are 3 on this side. 3 plus 1 equals 4. So we would expect to see 4 lines. And here you can very clearly see the quartet. And likewise, the 3H resonance for this methyl group, that methyl group has 2 adjacent hydrogens. 2 plus 1 is 3. And just as as simple spin-spin splitting predicts, we see that this is split into a triplet. So that's a very typical splitting pattern. To look at another one, so ethyl groups are very common, and they typically show up something like that, depending what the ethyl group is attached to. But that sort of triplet quartet thing is very common for ethyl groups. What about an isopropyl group? Here we have diisopropyl ether, so that's just an oxygen with 2 isopropyl groups. And I think you'll agree that there are 12 equivalent hydrogens. Well, why should I be so stingy? There's 12 equivalent hydrogens on the 4 equivalent methyl groups. So there's 2 equivalent hydrogens that are the ones left over on the carbons, on the ether carbons, so to speak. So we would expect a ratio of 12 to 2 or 6 to 1. And that's exactly what we do see. So these methyl hydrogens will all be split by the adjacent hydrogen over here. 1 plus 1 is 2. We'd expect a doublet. And that's what we do get. The 1H resonance, how many adjacent hydrogens are there to this unique hydrogen here? Well, 3 plus 3 is 6. 6 plus 1 is 7. So we would expect to see no fewer than 7 lines. It's not always perfect. We can't always see every single one of them. Sometimes the ones in the outside are so small that they blend into the baseline. I do believe as I stare at that I actually can see all 7 lines. So this is how you would be given information like that. Another type we'll say another type of hydrogen that you will run into. I want to be sure that we do some examples of aromatic compounds. This compound is P-anisaldehyde, which is paramethoxybenzaldehyde. So it's like benzaldehyde, but with an extra methoxy group para to it. And if we consider the types of hydrogens that are here, well, clearly you've got the 3 on the methoxy group. You've got the 2 hydrogens that are ortho to the methoxy. They're equivalent to each other. You've also got the 2 hydrogens that are ortho to the aldehyde group. They're equivalent to each other, different from the ones that are ortho to the methoxy. And then you have the unique aldehyde proton. Aldehyde protons, I normally look for at around 9 or 10 parts per million. That's exactly where this one is. It's around 9.7 or 9.8. Notice that it's still a singlet because there are no hydrogens on the adjacent carbon, right? So that's still a singlet. These 2 sets of aromatic hydrogens, and I'd be hard-pressed to say which was which exactly. You can look up anisaldehyde. I got this spectrum straight off that Japanese website. So you can look and find which is which. I would be hard-pressed to guess which is which. I do know that those are both the 2 sets of aromatic hydrogens, which I spoke about. There's 2, and then these 2. And each one of those is 1 adjacent hydrogen, so unsurprisingly, they are doublet split. And then finally, our methyl group integrates to 3 hydrogens, and it's also a singlet because there are no adjacent hydrogens. So that's very typical for a para-disubstituted aromatic compound. Now, things are a little uglier in monosubstituted aromatic compounds, especially if that one substituent group is electron donating, or at least not particularly electron withdrawing, like if it were an ethyl group, like an ethylbenzene. Now, really, there should be, besides the protons in the ethyl group, there should be, in principle, 3 types of hydrogen. These 2 that are ortho to the ethyl, these 2 that are meta, and then the unique para-hydrogen. But in practice, with compounds like this, when it's again an electron donating group, in practice, we can't distinguish those 3 types of hydrogens. They are technically different, but they're so similar that they just all fall on top of each other. And so this is something you need to be prepared for. Things don't always work out like a perfect fairy tale. But this is the spectrum of ethylbenzene. Again, I think you can see the triplet and the quartet, the 2H quartet and the 3H triplet for the ethyl group, with the exact same type of splitting as we saw in the ethyl group earlier. This time our CH2 is right next to a benzene ring, and here we are at about 2.6, very typical for protons that are benzylic. Whereas the methyl group is in a much more typical range for just ordinary boring alkyl hydrogens, right about 1.3, 1.4. Meanwhile, the 5 aromatic hydrogens just all fall on top of a heap here. And I just put here M for multiplet. So if you ever see multiplet, that's what that means. It means the splitting is not easily explained, and we couldn't even really explain it if we tried. So all 5 hydrogens in this case just sort of all fall on top of one another in a messy heap. That's not uncommon for this type of monosubstituted aromatic compound. And again, my recommendation would be to look up compounds with other functional groups. Look up some ketones, look up some alcohols, look up some, I don't know, alkenes. Take a look. It's the best thing you can do. I do want to point out, though I don't want to spend a lot of our time on it, that the spin-spin splitting phenomenon that we've spoken about so far is only the best case, only the simplest case. More complex splitting does sometimes happen. For example, we said that a resonance, like let's say for this unique hydrogen in 1,2-dichloropropane, what would we expect to see for that resonance? Well, it's easy to say there's 2 hydrogens here, there's 3 hydrogens on the other side, 2 plus 3 is 5, 5 plus 1 is 6, so it should be 6 lines. Well, not so fast. What we very well might find is, since these 2 hydrogens are different from the 3 hydrogens on the methyl, that they both split the hydrogen between them differently. And we might very well find that these 2 hydrogens split this hydrogen at first into a triplet, 2 plus 1 is 3, and then these 3 hydrogens in the methyl group split each of those 3 lines into 4 times each, right? Because 3 plus 1 is 4. So you wind up getting 3 times 4 is 12 lines. And you would come to the same answer, by the way, if you said that this methyl group would split that hydrogen into 4 into a quartet, and then these 2 hydrogens triplets split each of those quartet lines. So 3 times 4 is 12. Either way you do it, you get the same answer. And you might or might not be able to see all 12 lines. I would say look that up. That's 1,2-dichloropropane. Or you could look up 1,2-propane-diol. Should look rather similar. But I would not be surprised if you can see all 12 lines. Or you might not be able to see all of them. You know, they might fall on top of one another. In real life, I would simply tell you that that's a multiplet, meaning that the splitting is very complex. The worst case, the crowning audacity, is in the case of protons that are what we call diastereotopic. And we mentioned these earlier. These are ones that are permanently chemically distinct because they permanently have a different chemical environment. And one such case is in this molecule here, where I've even given you all of the assignments here. And the problem here is the CH2, these F hydrogens, or you could also really find it on these hydrogens that are marked C and D. Even though they're on the same carbon, at any given time, one of those hydrogens is going to be closer in space to this OH group than the other one. And so these 2 protons are not the same. They're chemically different. And you will see if you look here that they actually have different chemical shifts. They're somewhere in one of these heaps over here. And likewise, the situation could be really bad for hydrogen B, putting aside whether the OH hydrogen splits this one. Sometimes OH hydrogens cause splitting, sometimes they don't. It depends on a number of factors, like temperature, like concentration. The reason is that the OH hydrogens physically switch with each other. There's a physical exchange of those H's from one molecule to another. And so as such, that negates the splitting on the OH group. But you might find that this CH2, let's say, splits that hydrogen into 3, and then each of these splits first 3 into 6, and then 6 into 12. Once again, there could be a total of 12 lines. Now, you might not be able to see them all, but I would expect a complex multiplet. Bottom line on diastereotopicity. Again, I want to keep this as practical as I can. Basically, diastereotopicity is likely to lead to, and I've shown you how you can determine when it occurs in a molecule, right? You're looking for 2 hydrogens or 2 sets of hydrogens that are in the same carbon, but by virtue of being close to or far away from some nearby functional group, wind up being permanently chemically distinct. And so what this means for you practically is you'll see splitting that is more complex than you expected. I will end by saying that my story of diastereotopic protons in the research I do, especially most recently with the Singleton group, which I do over the summer, generally I only figure out, I'll be honest, I only figure out that protons are diastereotopic after the fact. What will happen is I'll make some compound, I'll go get the proton NMR spectrum, and I'll look, and it'll just be awful, just much worse than I expected. And I'm thinking, what's going on here? Is my compound not clean? I would have expected the spectrum to be much simpler than this. And then I look more carefully at the structure and I say, oh crap, these 2 sets of hydrogens are diastereotopic. So the splitting and chemical shifts are much more complex than I would have expected. Right, and I also, let me see if it's actually still there. One point I had also put in here, I was going to delete it, but I guess I won't. I had also given as an example 1-pentanol. It might not be the best example because as you can see, it's real hard to see the splitting in all of these things. But this is another example where you have diastereotopic protons, like let's say the protons labeled C. I would anticipate they might be diastereotopic, because one of them will at all times be closer to this OH group in space than the other one. So you might not see these simply as, well, I guess the splitting would already be kind of complex anyway, wouldn't it? Because there's non-equivalent hydrogens on either side. But the splitting might be even worse than that, even up to the point of those 2 hydrogens having different chemical shifts. So like I said, I don't know if 1-pentanol is the best example, but I've given you the spectrum as well as the assignments, so you can take a look at that. But just as with carbon NMR, just as with IR, the best advice I can give you is get in there and practice. Get in there and look at as many spectra as you can stand to look at and see if you can make sense of them. Don't start with huge molecules. Don't start with alpha-phenethyl alcohol. Goodness. Start with something smaller than that, right? And then gradually build up the complexity. So other than that, that will be it for proton NMR spectroscopy. We will continue on next week, I anticipate, with the chapter on carbohydrates. Until then, have a good day.